So it is good to see you again this week. So this week we are still in the fifth week of lecture. Okay, minggu kelima lecture. So basically, in this week we have already passed more than 80% of topic 2, which is about transformer. And hopefully today we will finish all of the discussion and the materials related to topic 2, and then hopefully from next week I can release another assessment, which is quiz 2, that will cover questions based on topic 2. Then also, if I have time, I also will release tutorial question for your exercise. Okay, so far in topic 2 we have just gone through all of the lecture without any assessment, without any tutorials being given. So hopefully after we finish this, from next week I will release some assessment so that you can do it at home. Okay, for today we continue. Basically for the topic 2 we have finished up to the exact equivalence circuit of real transformer. So I hope you can see this. If any problem with the sharing of this monitor, or which is if something which is problem at your side, just let me know. Okay, so we have finished up to the exact equivalence circuit of real transformer, and then from exact equivalence circuit we have go through another equivalence circuit, which is we call it as approximate equivalence circuit, which is something like this. This is referring to the primary side of the transformer, and the other circuit here referring to the secondary side of the transformer. And then we can do we can neglect some of the we can do assumption, so that we can neglect some of the effects of the excitation branch here, so that we can further simplify the equivalent circuit into the one without excitation branch or parallel branch. So this is much more this is what we call as what we call it as approximate RP XP are lumped together. So in practical solution situation, okay, we can neglect some exciting current that occurs at the this branch, so that we can further simplify. This one is the most simplified one without excitation, without the effect of the excitation current, which is the parallel branch here has been neglected. Okay, so there is no parallel branch for this one, for the sake of easier calculation. Okay, we can make easier calculation, easier representation of the transformer without parallel branch. Then now, so we have studied about equivalence circuit, in which we have a transformer. Then we want to do a study about that transformer, for example, in terms of calculation of the electrical quantities at the primary side and the secondary side. So electrical quantities is referring to the components like a voltage, current, impedances, right, power, and so on. So we can do further studies when we convert that transformer into equivalence circuit. So basically, when we prepare or when we try to draft a equivalence circuit, basically from the actual transformer, what we can do is to determine its components in terms of impedances of the equivalence circuit. So in this case, what we do is to carry out tests. Okay, basically in real world application also. For example, if you are a service engineer, for example, service engineer that do service of the transformer, what they do normally is they have some sort of instrument instruments such as not a multimeter, not a normal multimeter, but is which is more to sophisticated instrument like power analyzer, for example. Okay, they use the power analyzer to measure voltage, current, and also power of the transformer, which is I am talking about high voltage transformer lah. So they use that instrument to measure voltage, current, and power based on some others open circuit test ataupun short circuit test. Okay, so basically for the scope of work of a service engineer, one of the common thing that they do is to do the open circuit test and short circuit test of the transformer, so that they can study about that transformer. Okay, so basically in this case, so we do the open circuit test and also short circuit test of the transformer in order to determine the values of the inductances and also resistances of the transformer, including the excitation, the effect of the excitation branch, which is RC and also XM, right? So the first one we are going to study about the open circuit test. So what is open circuit test? So basically the arrangement of the open circuit test is something like this, as you can see in this figure, right? Transformer equivalence circuit. So we have finished this. I think this one. Okay, so open circuit test is basically based on this figure. We let the terminal at the secondary side open. Okay, as you can see, there is no connection to load or any connection or short, no short or connection to load, which is this is we left it as open like this. Okay, so what we do is to measure the values at the primary side, which is we place a voltmeter to measure the voltage across this supply. Okay, VT is supply, and then also the ammeter to measure its current, and then also the wattmeter to measure its power. Okay, then we will get power at open circuit, which is POC, and then also current at open circuit, IOC, and also voltage open circuit. Another measurement that we can do based on this setup is to measure the cosine theta, which is the power factor of this transformer lah. Alright, so once we do that arrangement, basically what we get from the measurement, which is from the experimental measurement, when we do the open circuit test from the experimental measurement, we basically can measure. First one is current, second one is voltage, and also power, right? So we have all of the values of VOC, IOC, POC, and cosine theta. So from the values that we get from the experiment, from the from the open circuit test, we can use this value to calculate the excitation admittance, which is YE. Okay, and then also the angle of the excitation admittance, meaning that, okay, for the circuit, for the transformer, which is something like this, in the open circuit test, we are going to measure the components of RC and also XM. Okay, so there is nothing to do about the series components, which is REQ and XEQ here, because in the series component, basically we determine it by using the short circuit test. But for the open circuit test, we just need to determine this, which is YE, okay, or RC and XM. Okay, all right. So our target for doing open circuit test is to determine YE and also angle of YE, so that we can represent YE in terms of its magnitude, and also the angle. This is the polar form of the YE. So after we calculate YE, we get the value of YE in terms of magnitude and angle. From there, because this is polar form, so that as we have learned in our previous session, that we can transform the polar form into the rectangular form. Okay, we can transform YE into rectangular form because YE will be equals to RC plus, sorry, YE is actually this is 1 over XE. Okay, the inverse of the reactance actually. So admittance is inverse of the reactance, which is equals to 1 over RC plus 1 over JXM. Okay, so once we get this, YE equals to in terms of magnitude, we represent YE in terms of magnitude and angle. We can convert this YE into rectangular form, so that from that rectangular form, basically we can determine RC and also XM. Okay, so basically our target is to calculate the admittance. Alright, so okay, this is the similar thing that I have explained earlier, which is YE is actually GC minus JBM. Why is that minus? Kenapa minus? Because earlier it was 1 over XM, 1 over JXM, right? So basically this part is BM. Then J naik atas, bila J naik atas, negatif J lah. Okay, so that sort of things. Okay, so that is why kita letak negatif. So basically ini pun sama lah. Ini pun sama sebenarnya. Further expand this GC and BM, kita nak dapatkan RC and also XM. So basically first thing saya ulang daripada asalnya, we do the open circuit test. Okay, this is the values we get from the experiment. Okay, we do the measurement using the meter, metering equipment to we let the transformer open circuit, and then we put the probe, then measure the voltage, current and power at full line voltage. Maknanya supply ni kita supply full voltage lah. Full voltage meaning that the voltage at the primary, contohnya kalau voltage tu 8000 lah kita bagi kat ni. Okay, supply voltage. Okay, kita supply full voltage, then we do measurement of open circuit voltage, open circuit current, open circuit power, and then power factor. So yang ni kita dapat daripada eksperimen. Okay, kita dapat value ni daripada eksperimen. And then barulah kita guna value ni untuk buat calculation. Okay, so macam mana nak buat calculation? Kenapa kita nak buat calculation? Sebab kita nak dapatkan excitation branch ni, impedance at the excitation branch, which is YE. Impedance, admittance, benda sama sebenarnya, tapi nama yang umum, the general name of the impedance is impedance lah. Basically admittance is inverse of the reactance, right? Okay, so we use these values to calculate YE in the form of polar form, and then we convert this YE into the form of rectangular form. Then finally we can determine RC and XM. So basically this is theory. It is easier for you to understand if you follow the example in the tutorial 2.2. If you follow this example in which I have uploaded the video that discussing about this tutorial, I think it is much more easier for you to understand, right? Okay, so once we have done this, actually that is the theory behind it. We want to find admittance and also the angle, right? So to find this is our target, admittance and also angle. Then finally we get in the form of this. I think what I do in this in my notes here, which is the same thing, which is benda yang ulang-ulang saja, tapi basically dia punya metodologinya macam tu ya. Okay. Alright. And then next is the short circuit test. Okay. So short circuit test, basically we have done this in the previous test, which is open circuit test. What we did was to find the admittance. All right, the admittance, which is the parallel branch. Okay. In the short circuit test, we are going to find the series resistance and also series reactance, which is series branch. Okay, no, there is nothing to do with branch, which is series element or series component of the transformer, which is in this case, we want to make sure that current will not flowing through the parallel branch. Okay, so we do the setup, which is we supply the voltage, which is quite low voltage, low voltage that pass through across the series elements here, across this resistance and inductance, and then we adjust the input voltage until current in the short circuit windings, in the short circuit part ni, current tu sama dengan dia punya rated value, meaning that if at the situation where this current is the same as the rated value, meaning that there will be no more current, which is there will be no more voltage across this parallel branch, no more voltage across this parallel branch. Okay, so basically apa yang ada voltage across series branch saja, series impedance saja. Okay, so from that we can do setup, which is very similar to the open circuit test. Kita pasang lah, we place our voltmeter, ammeter and also wattmeter to calculate the values of voltage, current and also power during the short circuit test. Okay, so from that short circuit test, basically we can measure voltage at the short circuit, current at the short circuit and also power during the short circuit test. So once we get all of these values, VSC, ISC and PSC, we can use this value, okay, we can use this value from experiment to calculate ZE. Okay, so ZE is the magnitude of series elements here, series components. Okay, ZE is basically REQ plus JEQ, JXEQ, right? So that is ZE. Okay, so we determine the magnitude of ZE for the series one, and then also the angle. The same thing what we have done. So previously in the open circuit, we determine admittance, which is a parallel branch. Okay. In the short circuit test, we determine the magnitude of impedance. Okay. Impedance ZE of series, series branch. Okay. Okay. Series branch of the transformer. So we get the magnitude of ZE and also angle of ZE. Once we have done that, we can represent ZSE ni in the form of polar lah. In the polar form, which is ZSE equals to VSC over ISC ni kita boleh determine based on the kita punya values from experiment. Jadi yang ni pula theta pula from our calculation. Okay, so basically I is lagging in this case. I is lagging. So when we do the calculation VSC divided by LC, then theta ni naik atas lah. Bila theta naik atas, maknanya 0 degree minus tolak negatif theta, dia akan jadi positif kan. Okay, itu teori saja. Itu teori saja because in the practical situation, this much more easier for us to understand by doing tutorial lah. Okay. Okay, so then from ZSE, we can determine further the series and parallel impedances, which is R and X. Okay, so from ZSE, we can convert this polar form into the rectangular form. Then we further do because this one, for example, if you want to represent the equivalence circuit that referring to the primary side, we can use this equation, which is we use the turns ratio, okay, to convert this into REQ and XEQ. Okay, so this is example of the equivalence circuit that we want to find, that referring to the primary side. If you want to find the equivalence circuit that is referring to the secondary side, which is for example, if you want to represent it in this form, okay, this one is referring to the primary secondary side, sorry. So we are going to use this equation. For this one, basically we use this equation because we want to refer it to the primary. Okay, it depends lah, depends on the question whether it is required us to do reference to the primary or secondary. All right, then next is about the per unit system. So open circuit test basically to find the admittance and angle. Okay, short circuit test is basically to find the ZSE impedance and also the angle. So the method is like that. So I hope that you can follow the tutorial 2.2 that I have shared with you just now. I have uploaded, but still processing the HD quality of the video. Just wait for the HD video to finish, then you can follow to solve for this tutorial, which is in this tutorial basically it is given a step down transformer with the values of Vp and Vs, and also the power of the transformer, and this transformer has been done the open circuit test and short circuit test to determine its values at the primary, and then short circuit test as well. Then we are asked to provide to find the impedance of the approximate equivalence circuit referred to the primary side and sketch the circuit. So basically, okay, please take note, in this question, this is not open circuit test at the primary actually. If you are referring to my tutorial notes, basically this is open circuit test referring to the secondary, and then this short circuit test is referring to the primary. Let me just show you again. Okay, I have made some amendment because this slide is not correct actually. When I check again in the textbook, Chapman's book, it is actually, this is referring to the secondary. Okay, open circuit test referring to the secondary, short circuit test referring to the primary. Okay, so this is the correct one. So follow your tutorial 2.2 or make correction here lah, make correction here. So this is not correct. what I should do. I think I can edit this. Primary. This is secondary actually. Like that. This is primary. Primary. So I think I can just make some corrections. So just back to this. Okay, it's close. Right. So basically, please make correction at your side. This is open circuit test at secondary, and this is short circuit test at the primary. Okay. So as you can see here, as explained earlier, in open circuit test, basically we supply the full line voltage. Full line voltage means that the full voltage that is at the primary side, which is 8000 lah in this case. Okay. In the short circuit test, basically we supply low voltage, but we adjust. We adjust the voltage so that current uh, current value is the same as the transformer's rating. Okay, the same as the transformer's rating. That is why it is not the same as 240, because we actually adjust the current. We manually adjust the current to make sure that current supplied is the same as the rating of the transformer current. Okay, so next is about the per unit system. Okay, so now about the per unit system. Basically, in transformer calculation, normally we use the per unit system. But it is not about transformer calculation only, but most of the power system based calculation is based on the per unit system, which is if you are referring to the our reference book, which is from Will D, Electrical Machine, Device and Power System, that I have shared with you in eLearn. There is a specific topic that discuss about the per unit system. Okay, so that is basically the per unit system, not normally used for the calculation of the transformer, but also in studies about transmission lines, studies about motor and the generator, which is the electrical machines, also discussed in this uh, course, right? And then also the power system. Okay, power system, power delivery system. Also, we use the per unit system in order for us to simplify the calculation, because if we use the conventional method, which is when we do the calculation of the transformer by using based on the reference, we refer to the primary side or we refer to the secondary side, like we have done in the example 2.1 before. If you follow my tutorial lecture or tutorial video discussing about example 2.1 here, basically on that, in that video only, it covers about 40 minutes. About 40 minutes I have to use to do to solve for this example 2.1 or tutorial 2.1. Okay, so there are a lot of calculation which is quite tedious in this case. Tedious means something that is difficult. Okay, something that need a lot of things, right? So in this case, to solve for that sort of tedious way of the calculation of the transformer electrical quantities, what we do is to use the per unit system, which is so this is basically another theory about the per unit system. So to understand further about the per unit system, we must go to the example question lah. So I will prepare another video discussing about the per unit system, which is basically discussed in this tutorial 2.3. Okay, so that I will share with you so that you can check on that video as well to understand about the per unit system. So basically in this session I will just explain theoretically. All right, I lost, where is it? Okay, here, right? Okay, so the what we do with the per unit system is actually what we do is to measure the electrical quantity. Okay, we have the actual value of the electrical quantity like voltage or current or power. Okay, and then we divide it by base value of the quantity that we have chosen. Okay, so the per unit quantity is actually actual value divided by base value of the quantity. Okay, in other words, it is a decimal fraction of some base level lah. Okay, so basically for the base, we choose the base. Uh, basically, what we do when we choose the base is we choose voltage or power, either voltage or power. Okay, so basically, we choose power. For example, P base or Q base. This is reactive power base. Okay, this is active power base. This is apparent power base. Sebenarnya sama sahaja. Okay, sama sahaja. Semua ni power. All of them are power. So we choose this as base because we know that this power is equals to V base times I base. So another quantity we choose as base is voltage. Okay, so saya punya ni asyik hilang. Okay, another quantity is V base. Okay, V base here, as you can see from my notes here. All right, we choose voltage as base and also power as base. Then once we know the V base and P base, we can actually determine the I base. So from I base here, we can determine I base lah. From I base, once we determine the I base, we can further determine the Z base. That sort of thing. We start with define P base or V base, and then from that P base and V base, we determine I base. From I base, we determine Z base. Okay, because V base we already know, right? Okay, so in this case, we choose power or voltage. Why is power is so preferred in this? Why we choose power as the preferred value or preferred quantity as base unit? Because for the transformer, as we proved earlier in our lecture related topic 2 as well, which is related transformer, power of the transformer at the primary side and the secondary side is actually the same. Okay, so power doesn't change. The values that are changed is either voltage. Okay, we step up or step down voltage, right? So the values that are changed in this case is voltage or current only. Okay, that is why we choose power, because power have nothing to do with the either it is at the secondary or primary. There will be no problem for us. All right, and then another value that we choose as base is voltage. So we choose voltage as V base, but voltage also in this case, we know that voltage change according to the turns ratio. Okay, so in this case, we choose P base and V base. So once we choose P base and V base, it is actually because V base we consider with the turns ratio. Actually, when we do a calculation in terms of per unit value, it is already cover the one that we have done before, which is the tedious one in our previous method. Okay, in our previous method that we transform Z. In our previous method, which one? we have done some elimination in this example, right? We eliminate receiving end transformer, okay, and then we eliminate the sending end transformer, right? So in that case, we do elimination of the transformer to represent it in terms of another equivalence circuit. But in this case, once we have done, when we choose the V base and also P base, actually we have already covered all those things. Okay, so there'll be no need to do the elimination of the transformer. That stages will be no need. Okay. Okay, so for further clarification, further understanding of about this per unit based calculation of the transformer, we will you will have to follow the discussions or the tutorial 2.3 that I will upload the video later. Okay, so that one is about per unit system. So we have finished the components of the impedance calculation based on transformer open circuit test, also short circuit test to represent the equivalent circuit. And then the second part in this session, we have discussed about the per unit system measurement of the transformer, because we are going to use this per unit system in the transformer calculation, which is much more easier compared to the previous method, which is the conventional method. We have to do some elimination of the transformer at the both sides, receiving end, also sending end. But for this case, there will be no such tedious procedures in calculating the transformer values in terms of its electrical quantities. All right. So now I'm going to talk about the voltage regulation of the transformer. This is basically another theory about voltage regulation. So basically, in a large size of transformer, for transformer like this, for example, is as you can see, basically at the primary side we supply constant voltage. Okay, we supply constant voltage, but at the secondary side, okay, because at the secondary side normally we will connect with load. Okay, at the secondary side, Vs here, we will connect with loads. Okay, sometimes we have heavy load, sometimes we have light loads. It depends. So this Vs actually varies. This Vs actually berubah-ubah lah, disebabkan load, disebabkan value of load. Kadang-kadang ada load yang besar, ada load yang kecil kan. So Vs is varying, so it depends on loads lah. So in that case, for example, if I connect heavy load, saya sambung pada secondary part ini dengan load yang besar, so what happen is the voltage will be drop. So voltage will drop at certain value lah, in terms of percent, berapa persen voltage to drop. So meaning that what I am going to do is to support for that drop of voltage, okay, in transformer, because at the secondary side that transformer is connected to a heavy load. Okay, so in some situation the voltage will be dropped. So in order for me to compensate, I use the word compensate, or to support lah, to support voltage of that drop on that voltage, saya kena buat voltage regulation. That is what it means by voltage regulation. So basically we can calculate the voltage regulation using this equation. Okay, for the full load voltage regulation, basically we use this expression, which is voltage at the secondary during no load, masa tak ada load, okay, tolak minus voltage at the secondary during full load. Maknanya minus voltage value during full load, meaning that during full load normally voltage value will be much more lower. Okay, contohnya at the secondary sepatutnya dia punya output Vs adalah 240, tetapi bila kita bagi load yang besar, okey, voltage tu akan drop. Maknanya bukan 240 lagi lah, mungkin dalam 210 ataupun 200 volt saja. So, maknanya VS ni yang no load, masa tak ada load, tolak dengan yang ada load, maknanya yang full load. Full load. Bukan full load, full load. Okay, divided by voltage at the secondary during full load. Maknanya kalau kita istilahkan menggunakan max tadi, value tadi, contohnya 240 tolak dengan 200 bagi dengan 200 lah, darab dengan 100%. So we will get lah how much in percent the voltage that we need to add. Maknanya kita kena supply lagi lah voltage supaya kita boleh make sure that at the output VS itu stable. Okay, VS itu still maintain at that 240 for example. Okay, so voltage at the secondary during no load ni sebenarnya kita boleh menggunakan because we know that VP is AVS, which is the turns ratio here. So we can further expand this equation. We substitute VS dengan VP divided by A, kita dapat macam ni lah, bentuk yang macam ni ya. So kalau dalam bentuk per unit, okay, kita dapat yang macam ni lah. Ini dalam bentuk yang per unit lah. So yang per unit sudah tak ada A ya. No more A ya, tak ada A dah. Sebab per unit lah, kita dah represent the values, all of the values. Kita dah consider awal-awal dah dia punya turns ratio tu, kita represent dalam bentuk base. Okay, so there is no A ataupun turns ratio for the VR in the case of per unit representation. And then basically for the ideal transformer, okay, for the ideal transformer VR is 0% lah, because we consider no drop in voltage, no loss kan. So basically we can consider for the ideal transformer representation of the equivalence circuit, for example, when we do the calculation, it is perfect, which is 0% voltage regulation. There is no need for voltage regulation lah. Kita beranggapan voltage tu tak drop lah bila kita supply dengan full load pun dia tak drop. Okay. Okay, so basically VR is how much voltage that is required to compensate the drop of voltage during full load. Alright. Okay. So lastly, about transformer efficiency. Okay. Similar to the motor or generator. Okay. When we talk about input and output of the system, when we talk about something like which is transformer, is the same. Transformer is two-port system. Two-port input, two-port output. Kan? Ni katalah black box kan? So transformer we imagine something like this. So bila ada benda, tak kira lah mesin lain contohnya generator ke motor ke, dia ada input dan output kan. So bila ada input dan output, of course kita nak measure dia punya performance, kita measure in terms of efficiency. Alright. So TR efficiency, which is transformer efficiency, represented by mu ni, which is P out divided by P in times 100% lah. Okay. So sometimes P out ni bukan dia P out saja, it is not perfect, because during transfer of power inside the transformer itself, it occurs some losses. Okay, dia berlaku loss. That is why P out ni kadang-kadang kita kena consider lah loss. Okay, kita kena consider lah loss. P in sebenarnya P out tambah dengan loss. Okay, so yang ni lagi further extended punya equation lah. Maknanya loss tu lagi detail lah, in terms of copper loss, in terms of core loss, eddy current kan, eddy current loss dan sebagainya. Okay, P loss ni VSIS cosine theta. Okay, so itulah, tak ada dah. Okay, so itu saja 3 bahagian yang kita nak discuss hari ni secara teori. Okay.